Hello, my dear students. I am B S Pandey. Today we are in lecture number 67 of Standard 12th. We are studying chapter Electromagnetic Induction. Okay. Today we will start our lecture with some numerical problems and then we will move to the eddy current and self-inductance and induction. So, let me start today's lecture. It is lecture 67 of Chapter 6 NCERT Electromagnetic Induction. This chapter is very important, my dear students, for the alternating current chapter. That is, after this we will study. Okay, so be careful. Here, the first question we are going to deal here. Let me make this particular question as a theory, because in previous years CBSE had asked this particular question in derivation. Okay, EMF due to rotating spoke of cycle. You know that a spoke of cycle, it is straight like this way, and this is the center, that is the axle of the cycle. The number of spokes are provided. Here we are considering for the one spokes. Okay, we will get the answer, and to find the EMF due to the different spokes, we will multiply with the number of spokes. Here, one spokes we are considering. Now it is given in uniform magnetic field. This is the uniform magnetic field B, in which this spokes is, that is the system is kept. The uniform magnetic field, it is B. Remember, my dear student, here this is the rim of cycle, metallic rim, and this is the spoke which is pivoted at the center, and it is allowed to move with the constant angular velocity omega. Here omega. You have to find the EMF induced between the center and the circumference of this rim. Okay, you have to find the induced EMF. If you have the resistance, then you can find the current induced also. But the basic thing, you have to find the EMF induced. Once you will find the EMF induced, then you can find the current induced also. How you will solve this question? Students, we have studied the motional EMF. What we have studied, the motional EMF, E induced, it is BLV. All right. Yes, this equation we have studied. BLV. Here, this entire spoke in motion, but we know that here the each element of the spoke, each element will have the different velocity. Actually, this point at the edge of the spoke is moving with the R omega. V, it will be R omega. V, it is R omega. Here R is the length of the spoke. Suppose the length is given L. L is the length of spoke. It is given. Now, then the speed of this tip will be V equals to R omega. Am I right? Yes. But as you will move down, the speed will decrease. In fact, the speed of the spoke element at center, it will be 0. Here the formula in which we are having the V, it is constant. Okay. But here we can see the velocity of each element is different. Then what will do? Of course, the B will be uniform and L, it is the entire length of the spoke. Then how we will solve this question? So we will take integration, help of integration. Okay. At certain length, cut an integral length, it is dx. Okay, at x we cut a value dx. Now we are having a spoke of length this much only, and this is dx. Be careful. What will be the velocity of this one, my dear students? So the velocity, since it is at a distance of x, so the velocity of this elemental spoke will be V equals to r omega, and r here the x and omega for each element is constant, so it will be the x omega. Now we are having the velocity, length of spoke, how much it is, dx, b it is uniform, so we can write here for the very small elemental spoke the EMF will be very small. Suppose it is dE and it is BLV, BL it is how much, the length of the spoke it is dx, and B how much it is, x into omega. By integrating you will get the total value. We know that at this point where the x is 0, velocity will be 0, so the EMF induced will be 0, and the total length we get at this point it is L, and the EMF will be maximum, it is E. Now get the integration, it is very simple. B and omega are constant. Now x dx from 0 to x, b omega x dx will be x square by 2 from 0 to, I think this should be L, from 0 to L, so the E is equals to 1 by 2 b omega L square. This will be the induced EMF. Try to see carefully, you will get this thing. This is not very tough and I used to explain very slowly. Now the next question, my dear student. Here, this will be the question as well as derivation, mathematical expression. You will find a number of questions on the basis of this one. My dear student, if there will be the two spokes, what will be? Suppose if two spokes, you can find the direction of induced EMF also, in which direction the EMF will induce, in upward or downward direction. Okay, to find the direction you will use the vector form. Here if the two spokes, suppose the one spoke here we got and we are getting the EMF E. To represent this E, I am drawing here a battery. I am connecting here a battery. Okay, here suppose if there will be the two spokes and this, if ring is moving, okay, the two spokes, what will happen? Here another battery will come. If three spokes, here another battery will come. If four spokes, another battery will come. In this way, you can see the number of spokes will give the number of battery, and all the battery will be connected in parallel. You can see all the battery, it will be connected in parallel. Okay, now the entire value you can find out. Now the next question, my dear students. Here in this uniform magnetic field, if a rod is moving with particular speed, this rod of length L is moving with particular speed B, the magnetic field is uniform, which is B, and you have to find the EMF induced between two ends of this rod, then what will be the EMF induced? The very simple, we have studied, it is E induced is equals to BLV. Alright, so the B is given, length is this one, and V, this is the answer. On the basis of this one, it was only to recall you, on the basis of this one I am going to ask a question. Now this rod is being given so that it has two sections. Okay, the rod has two sections and the two are inclined at certain angle. In this uniform magnetic field, rod is like this way. Okay, and here the velocity is given V. The rod is making an angle theta and here an angle theta. Length of rod is suppose A and this is the rod of length A. This entire length is 2A. Okay, and it is the velocity given perpendicular to this rod, it is V. Now between this two end of this entire system, the rod, what will be the EMF induced? You have to find how you will solve this question. Okay. So my dear student, we know that if the rod will be in this way, suppose if you are taking any rod in this way and you are giving the velocity v, remember there will be no EMF induced between these two ends. E induced will be 0. Why, sir? Because as this rod will move, there will be no flux cut out, there will be no area swept out by this rod. If this rod is moving this way in this magnetic field, there will be the flux changes, but here in this case the flux will not change and the EMF will not induce. But here, remember, as this rod is moving in this uniform magnetic field, you can have the two component of this rod. This will have the two component, one along this one and along this one. But this component in horizontal direction will not have any induced EMF, and this component which is perpendicular to this horizontal one, that is the vertical, which is A sine theta, okay, will be induced by some EMF. And in similar way, there will be the A sine theta, this one also. Now, what will be the entire length of the rod? So, the entire length of the rod, it will be, total length, it is 2A sine theta. Now, it's very easy. Now, you can write the answer directly. E induced, it is BLV, and the B it is uniform, and L becomes 2A sine theta, and B it is given B. So this is the answer. Okay, my dear students? Yes. Now one more question. It is very important to solve the question, my dear students, of this particular chapter. Now, next question it is, you are having two coil, identical coil, not identical actually, totally, but the two coil you are having. One, it is of copper and another, it is of aluminium. This question was asked in board. These two are placed in uniform magnetic field. Individually, we are studying, remember, there is no relation with this coil to this coil. Individually, we are considering. But the field are uniform. Here the magnetic field is B and here the magnetic field is B also. These two rods are rotating in this way. These two rods are allowed to rotate with omega. Sorry, I'm telling the rod. Ring. Okay. Omega. The radius is same. The magnetic field it is given the same. Of course, the cross-sectional area will be same. Mass of the rings are same. Now the question, you have to compare the EMF. Compare the EMF and I induced in two coil. Okay, number of turning it is 1 for both the coil. How you will solve this type of question? Okay, so let me solve this type of question. My dear student, if magnetic field is B and suppose area of this coil it is A, alright. So in this direction, if the area is, then good. At any time t, any time t, it will rotate by theta, alright. And this theta can be written as omega into t. Am I right? Yes, it is omega into t. Now, we have to find the induced EMF, and to find the induced EMF, we know that we require flux. After that, we will get the change in flux and we'll have the induced EMF and current. So, resistance of both the, resistance, it is not given. So, here the flux will be B dot A, which is BA cos omega t at any time t. It will rotate. The theta is not uniform. It will increase, decrease. All right. So the BA cos omega t. Now E induced we can write minus d phi by dt using Faraday law minus d phi, it is BA cos omega t divided by dt. And we know that we have solved this type of question, my dear students. If any ring is rotating inside uniform magnetic field, it produces alternating current, increasing, decreasing. Okay. So this will be B and A are constant, and cos omega t will be the minus sin omega t, minus and plus. So the omega sin omega t, this is the induced EMF. Okay. Now you can see B is constant for both the coil, A is constant for both the coil, omega it is also constant for both the coil. It means in same time both the coil will rotate same. So this is constant. EMF induced in this coil and in this coil will be same. Now come to the next part. It is the current. We have calculated the EMF induced. Now the current. Okay. So the current, we know that it is E induced by R, and we can write E induced by R, it is rho L by A. Could you write? Yes. So the I is equals to EA, this is the induced, divided by rho L. Okay. The length of this particular wire and this one, we know that it is same. Resistivity, but the resistivity will change. We know that resistivity of copper, it is less than resistivity of aluminium, because the copper is good conductor compared to the aluminium. It means I is here, I is inversely closer to the resistivity. You can see. So the current induced in copper, will be larger compared to the aluminium. No induced EMF will differ, but current induced will differ, and this copper will induce more current compared to the aluminium one. Okay, this was the question to compare. Now one more question. There is a question in NCERT, my dear student. You will find the wings of an aeroplane which is moving under Earth's magnetic field, and you have to find the induced EMF across the two ends of the wing of aeroplane. And that question is not very tough, my dear student. You can solve. I know that. That's why I am dealing here the another type of question. Here, this is the very, very important question. Okay. A coil is kept here, rectangular coil, and this is break at any point. This is not complete. Okay. And it is kept in a uniform magnetic field which is produced by this coil. We know that if the current will move, okay, this will start production of magnetic field. And this particular rectangular coil, whose dimension it is given 8 centimeter and 2 centimeter. All right. It is in a stationary state. It is in stationary state. Why? Because there is no current induced, no EMF induced, and it is in stationary state. Okay. Now, the resistance of this coil, if it is, you can say, suppose any value, R, it is 1.6 ohm, might be differ from the book. I have seen this question in book. 8 centimeter, 2 centimeter, resistance is given 1.6 centimeter. Now, the magnetic field is being established initially when this was break. that is the initial magnetic field, and this is 0.3 Tesla. Alright, but once this coil is connected to make a loop, the current used to change by any means or method. Current start changing, so that the magnetic field goes on decreasing, and this magnetic field decreases with the rate dV by dt. It is minus 0.02 Tesla per second. In 1 second, this much amount of magnetic field is decreasing. Okay, I hope this question is very clear. Now the question is, find power dissipated here by the coil in form of heat. The question, find power dissipated in form of heat. This is the question. How you will solve this question, my dear students? So look at here how to solve this type of question. We know that to find the power, we are having the formula either I square R or V square over R. It means we have to find either EMF induced and current induced. But to find current induced, we are having the resistance. First, we will have to find the induced EMF. So why not we try to find induced EMF first. Induced EMF by this coil, remember, it will be E induced by this coil. First we need change in flux, and the flux, it is B dot A. Alright, and E induced, it will be minus dBA by dt. Here remember, the coil is constant, it is not moving, but the magnetic field is changing. That's why the flux changing and EMF induced. Here the A is constant, the minus sign I will take. A is constant, but this magnetic field is changing, so the dB by dt. In question, it is given area and the rate change of magnetic field also. So you can write the value directly from there. A, it is 8 centimeter and 2 centimeter product. In SI unit, you can write 10 to the power minus 2, 10 to the power minus 2, minus 4, and it is 16. Alright. Yes. A, dV by dt directly it is given. This dV by dt it is given minus 0.02 Tesla per second. You will put the value. You have E. You have calculated here the value of E. Now the resistance is given. By doing some simple calculation, you can find the here power dissipated by the coil. In fact, in question it has been asked, what is the source of power dissipation? So the source of power dissipation, it is the change of magnetic flux by the coil. You can write. One more question it is used to ask, my dear students, in board, in that motional EMF, if you stretch the wire, slider, let me draw here. Here the slider, try to recall, in last lecture I have told, if you slide this slider with the velocity v, okay, here the current induced and energy and power induced, we know that the energy can never be, okay, produced. Then whether this violate the conservation of energy, the law of conservation of energy, and this was the question. So try to understand whether this production of energy in this coil is violating the law of conservation of energy, my dear students. Okay, now come to the next topic, and it is eddy current. Give the heading eddy current. It was well explained by Foucault, that's why this is also called Foucault current. Eddy, it means whirlpool. Eddy, it means whirlpool. That is the chakkar. Alright, bhavar. So this is the whirlpool. Eddy, it means. Eddy current we are going to study. How this eddy current produces. This is also current called the Foucault current. One of my students asked, sir, how this EMF induced in a coil when flux changes even there is no connection with any source? Of course, it was the very fantastic question. Actually, I forgot to explain in lecture. If this is magnet north pole and there is no such contact between this magnet, even it is not supplied by any source, this is the LED bulb and it start glowing. How it is possible, sir? So my dear student, I explained that student, this coil is a conductor and the conductor having the free electrons. Alright, and this free electrons can move within the conductor. We know that if any charge projected, if this is the magnetic field, and if you will project any charge, you must remember and might have been remembered, if you only project any charge inside the magnetic field, what happens? It start moving in the magnetic field in a circular loop. Here the circular loop, it is made by the charge because it is compelled to move. It is not compelled to move in a particular manner. Here only it experiences a force and start moving. Okay, the thing I want to explain from here, if any charge will move inside the magnetic field, it will experience a force, and vice versa. That is, if any charge is in static state, magnetic field will vary, that is, the magnetic field will move, then the charge will again experience some force, and due to that force, charge will accelerate and it will gain some drift velocity, and that drift velocity actually start inducing the current and EMF. In same way, here the EMF induced in this coil due to motion of charged particle. But my dear student, suppose if you are having a metallic sheet, try to think, if you are having a metallic sheet in which electron can move in any direction, the free electrons are there, this is the metallic sheet, okay, and here the strong magnets are kept. Suppose this is the magnet. I'm sorry, the disturbance was there due to the fan. I have switched off now. Here, suppose magnetic field, if you made a coil, electric coil, here the current, and the current is changing, due to change in current, the magnetic field through this plate, it is changing. Right now we have solved one question also. But this is the plate, remember, this is the two dimension, it is the plate. What will happen? Due to change in this magnetic field, there will be the flux trapped with the plate, it will change. And due to change in the flux trapped with this plate, what will happen? There will be the number of free electrons, the free charges, and they will start moving. Due to the motion of individual charges, there are number of loops start making, but they all electrons start inducing the loop of other electrons, and after a while, it takes very small time, but after a while, all the electrons start moving in a particular orientation, and that orientation makes a big loop or the loop in a metallic coil. It means if there will be a current loop, there must be some current in this metal plate, and that current is called eddy current. But remember that eddy current must be in a closed loop, because due to this magnetic field, the charge will always move in a circular path. Alright. So this type of current is called eddy current or the Foucault current. how this is producing? Remember, either plate is moving in uniform magnetic field, the field is uniform, it is not changing, plate is moving, oscillating, or the plate is in a static state and the coil is also in a static state, but the field is changing. In both the case, it means overall there will be a relative motion between the source of field or the field and the metallic plate. There will be the induced EMF. Alright, my dear student? Okay. Now you can write the definition of this eddy current. Okay. So eddy current you can write due to change in magnetic flux and relative motion between the source of field or the field and metal plate and current and EMF induced in the metallic plate, it is called eddy current, and the EMF induced or the current induced, it is called the eddy current. Try to understand with this diagram. Here I am having electromagnet, suppose the north pole, and here it is south pole. Okay, the field will be from north to south, and we allow to oscillate a metal plate here. A metal plate is oscillating in this uniform field. Okay, this is oscillating in this way. As this metal plate will oscillate, this is the metal plate. As this metal plate will oscillate in this uniform magnetic field, which is formed by these two poles of the magnet, what will happen, my dear student? There will be a current induced, as I have discussed in very detail, in a particular manner. In which direction this current should be induced, you can find using the Lenz law. If it is moving in, the flux is increasing. So for this phase, if the flux is increasing, it means suppose the south pole is going near to the pole, and the south pole will give you the direction of this one. Why? Because this will induce a current. There must be some damping also. Why this damping? Because this coil is try to freely move inside the field. As it will come into the field, the flux will increase, and due to that increase in flux, it will induce the same pole as it is and start repelling, so its velocity little bit decrease. As it will leave the field, remember, as it will leave the field, there will be the change in direction of current again. So current in this direction start forming as it oscillates in and out, and this current is called the eddy current. You can say, my dear students, in very small time interval, this current actually changes its direction after every oscillation, and due to that change in current, of course, the direction of electrons, motion of the electron is also changing. There will be the huge collision between the electrons, and heat energy will release. Actually, this is used, this particular thing, it is used as the productive work. Its heat develop, it is used as a productive work. The application of eddy current, you can remember, you can also decrease the eddy current, that we will discuss in next lecture. But you can write the application of this eddy current, my dear student. There are the number of application, it is mentioned in NCERT also, like the magnetic braking, okay, induction furnace, and you can write the metal detector, that we will study in next lecture. I will explain you the working of metal detector, and then I will start the self induction. Okay, so these are the in electric meter, it was the very previous, the manual electric meter, this concept was used. Okay, and the electric damping, you can say. So these are the application of this eddy current, my dear students. You can study in NCERT. So this is all about the today's lecture, my dear students. We will start the next lecture with the self-induction and mutual induction. Okay, thank you very much.